Point one, you get heat stroke. Anybody ever had heat stroke before? Borderline. I had a borderline issue too, because I tried to be like the knight in shining armor and get out and help this girl in college push her car halfway up a hill to get to a gas station because it had died. A friend of mine was just watching me the whole time, so she came out, picked me up, drove me back to her house, where I proceeded to spend the next 45 minutes lying down on her bathroom floor in the dark, just going, ugh. Yeah, that's borderline heat stroke. Here's our normal range for temperature. Above that you get fever. Above that you get hyperthermia and death. Why? Why do temperatures kill us? Allow me to rephrase. Why does cooking an egg make it change state? Yes, because the chemistry that makes up our body has certain physical properties. And if you add a lot of heat to those chemicals, you can induce either physical or chemical changes. And if they are no longer doing the job that they were doing, the job that we count on them doing in order for our bodies to survive and continue, then we die. Why does your body go into fever? Fever is a reaction most of the time. It's a good reaction on the part of your body's immune system, because here's the thing. You have evolved a mechanism where up to mild degrees of fever, your body can still function. But guess what happens to most bacteria? If not kills it, it makes it very difficult for that bacteria to grow.
This is why your doctors say don't give your children, let their fever.
Right, if it's a mild fever, let it do its job. The fever is there for a reason. Your body can do just fine. It activates heat shock proteins that will chaperone your body so that it will still function relatively normally, but certainly enough to survive, but it makes life really uncomfortable for those bacteria.
You shouldn't medicate a child's fever until it's over 102.
Unless, of course, you're trying to be a bad parent because you have to go to work and have a really mild fever and you don't want to get sent home from their daycare, in which case you medicate them just to gloss it over, completely ignoring the fact that you're being ethically inappropriate and just spreading whatever it is your kid has to all of the other kids. But then you just rationalize it because everybody else does it too, and they deserve to suffer. Yeah, exactly.
I get that all the time. They're like, oh, they weren't sick when I brought them.
Yeah.
They just developed this huge fever for
Right,
themselves.
yeah.
Right.
It's just because the Tylenol wore off.
Yeah.
Exactly.
I don't know what you're talking about.
Herd immunity's becoming
I've totally never done that before. Hypothermia. What was the last one?
Hyper.
Hyper. Meaning more or above. Hypo meaning less or below. Hypothermia is when your body temperature drops below that normal range. So 28.5 degrees C. We provide oxygen-increased blood volume with saline fluids, and this was new to me. Injecting warm fluids into the peritoneal cavity makes sense. It's like literally, let's just give you a warm fluid bath in your gut region where there's all that surface area to absorb all that heat.
Well, it's because that's your core.
Yeah, exactly. Well, that's what needs to be warmed up. But it's also the same thing. Okay, here's the thing. Where does ice melt? Think about this. You got your Wendy's ice cubes, which are honking huge. You've got your Sonic ice, which is shaved. You ever notice that? You guys eat out, and is this me? I eat out every too much?
You can buy it in bags.
Shaved ice?
Sonic ice.
Yeah.
So, Sonic ice is shaved. It's the little pellets. It does a great job of making your drink really cold really fast, but it also does a great job of watering down your drink really fast. Ice melts at the surface. Big ice cubes. They don't just go, they get smaller and smaller and smaller and smaller and smaller and smaller and smaller until they're gone. Because the surface is where there's heat exchange. The surface is where the warm things heat up the cold things, making them warmer, exposing the things just beneath them. Shaved ice melts fast. It cools off the thing around you fast. If we need to warm up your body, you have a limited amount of surface area here. What's another way to make you warmer faster? find a way to expose a whole bunch more surface to something warm. We've got a lot of surface in here. They also happen to be, aside from this thing, the things we need to keep from freezing and failing. But yes, there's a bunch of benefits. But still, I'd never even thought of that. Like, well, that's a neat trick.
Well, when you're cold too, your blood automatically goes to
Right.
your core and your brain anyway.
Yep. The blood is sequestered away from the skin, which is one of the reasons why drinking alcohol, even though it warms you up when you're cold, is also threatens your life, because alcohol is a vasodilator, which means that it opens up your blood vessels in your skin so that all that nice warm blood that your body's trying to keep next to your heart and your brain slips out to your skin where it can get cooled off, and so it makes you feel warm, but it actually kills you a lot faster.
You don't realize you have hypothermia if you're drunk.
Yep. Alternatively, hyperthermia, this guy right here, that's the problem that you have if you were to, say, partake in something called ecstasy and then go to a rave or other party where you might be gesticulating in a manner that it uses a lot of physical energy. Because one of the things that E does is it cuts off your ability to sweat.
Yeah, and you overeat.
And you don't notice.
Well, the thing is too, is people drink whenever they take.
Yes.
And so then all they're doing is dehydrating themselves even more, which makes them they end up having a heart attack.
Right.
Because you dehydrate yourself from
And
the
you get too
alcohol
hot.
and the X, and then you get too hot and you
Yep.
go swollen.
But alcohol can be miscible with water. The proper ratios will actually lower your freezing point, so you can get a lot colder.
No.
No.
You might be able to get a little bit colder before you froze,
Yeah.
but you'd be dead before you got there.
Yeah.
That's the problem.
You'll see a lot of that in the hospital.
Although, if you live in really northern climates, there is a phrase that they have in ERs, you're not dead till you're warm and dead.
Yeah.
So, let's talk about energy. We're not going to get through this chapter today. We're getting too sidetracked. Sorry. So, identify energy as potential or kinetic and convert it between different units of energy. So, energy, we've already talked about it a little bit. Temperature is a measure of energy, right? It's one of the reasons why I didn't like that oversimplification. It is a measure of energy. Energy is otherwise defined as the ability to do work. Kinetic is energy of motion. Potential energy is from the position or object. I don't have something that is easily droppable, so I'll just say let's pretend for a moment that you hold something up and then let go of it. The amount of energy that it has, the potential kinetic energy that it has, is greater when you hold it higher because there is a greater distance for gravity to have an effect on it as it moves. Therefore, the potential kinetic energy is greater in an object held high than one held low. Where does that potential kinetic energy come from? The fact that you burned a lot of energy to move that object against the force of gravity. Or something else did. But what I just told you was that potential and kinetic energy are interchangeable. You can impart potential energy into an object by exerting kinetic energy into it, which can then be converted back into potential energy if you let go of it, as gravity reactivates it, accelerates it, and it moves down. Creating the always fun game for children to play of dropping a ball on your lower sibling's head. Insert any number of other objects for ball. We all know about potential energy with respect to gravity. This is something that we have seen illustrated to us over and over and over again, proven to us, if you'll forgive the inappropriate use of the P word in a scientific class, over and over and over again in our lives, i.e. the aforementioned game between two young children. And yet the thing is, this potential energy, why does all that water have all that potential energy? Because we spend a whole bunch of energy building this dam to force the water to build up behind it, so that we could take advantage of all of that potential energy of water at an elevated state, so as it flows through this system and possibly through a channel system, we can take advantage of all of that energy to turn a turbine and get some electricity. Or maybe we just made this dam because we were tired of floods. Who knows? But This is potential energy, which can be converted to kinetic energy. There is another form of potential energy, which we'll get to in a minute, but I want to mention it here because I'm harping on it so much, and that is potential chemical energy. Give me a metaphor for a dam that uses a plant and has nothing to do with water.
Carbohydrate, sugar.
Sugar. A plant takes carbon dioxide from the air, it takes water from the air, and with the addition of energy from the sun, it turns it into a molecule of sugar that is in no way special or more special than the carbon dioxide or water that it started from. Except for the fact that that new organization of molecules stores some of the energy that that sunlight used to contain. And when you eat that plant, you can break that sugar down into into carbon dioxide and water and capture some of the energy that was released. Every molecule of sugar is literally a tiny chemical battery that stores sunlight just for you by whatever creature or plant it was that you ate in order to get it. That potential energy is just as real as this. And we will do math to prove it. Heat, the energy associated with the motion of particles. Heat is measured by what physical property we have discussed? Temperature, right? The SI unit for energy and work is the joule. That little K behind that big J stands for what? As a prefix? Kilo. So a kilojoule, kilo means 1,000. A kilojoule is 1,000 joules. So you can turn that into a conversion unit, right? Any equality can be turned into a fraction that equals 1. So you could convert between joules and kilojoules. Could you convert between joules and millijoules? Yes. A comparison of energy for various resources that we use. Energy used to sleep for 1 hour, around 10 to the 5th joules. Energy from 1 gallon of gasoline is around 10 to the 8th joules. Seriously, I had, you know how you're supposed to get fresh gas, every year? So I had, it wasn't even 1/3 of a gallon of gas left over from, we had a riding lawnmower, and so I had this gas left over, and so it was coming up on spring, summer, this few years back, and I had this old gas, and I don't know, I don't want to just throw this into my lawnmower because it's probably separated out with the ethanol and stuff, so this is probably not good, so I'll just get rid of it. Well, you shouldn't pour gasoline out. It is bad, contamination. You should properly dispose of your gasoline, or you could use your gasoline for what it was intended for in the first place, which is to just burn it. Well, I didn't have a lot of leaves to burn, so what I did have was a big copper bowl for a fire, like a fire pit bowl, right? And so I was just like, oh, this is neat, so I just poured a little bit just to cover the bottom of the bowl in, and then I knew that this would be dangerous, so I stepped back and took a match and tossed it in there. And you got the effect of whoosh, recorded this on my phone, you got that neat little whoosh, and then it just kept burning for a really long time. You don't realize how much energy is in some of this stuff until you burn it. When I was in high school, I went camping with my parents, and we didn't have any fire starters, so we just used some Doritos. Holy balls! Doritos! You light a Dorito, it will burn for a long time, really bright, and then you realize, I can eat a whole bag of those. And then you realize, why I have such a rotund stomach? Because all that energy that's in that Dorito, that's in you now. Well, not all of it, but a lot of it. Solar energy reaching the Earth in 1 second. 10 to the 17th joules. You ever wonder why solar power is the way of the future? If we could just get good at doing it? Seriously, we suck at solar power. Plants are 10 times better than us. They've also been around for millions of years longer than us, so you would hope that they are. But still, if we could capture a fraction of this, leave your lights on all night, yo, it doesn't matter. The sun will make more tomorrow.
Our biggest problem is not capturing the energy and storing it.
It's both. But yes, if we had better storage things, then our technology would be good. But still, we are a fraction. The amount of energy capture that we get from, let's call it the average solar cells, is still a fraction of what a tree does. Photosynthesis is an incredibly efficient, and even that only gets a fraction of the amount of energy that touches it. Most of the sunlight that a tree absorbs, it absorbs as just heat. It just warms the tree up, just like it does when you stand out in the sun. But still, plants are so much better than we are. Energy consumption for 1 year in the United States, 10 to the 20. So do the math here for a second. All of the energy used in the United States is 10 to the 20th in joules. How many seconds would it take if we could capture 100% of the energy that hits the Earth from the sun, which we shouldn't do because then the Earth would get really cold really fast. But if we could, how many seconds would it take to power the entire US for a year? 1,000. 20 minus 17. 10 to the 3. Seconds. That much sunlight would power the US for a full year. If we could capture it all. What's this number up here at the top? The energy radiated from the sun every second. Why is that? Because the Earth is really tiny. How much of the light that's emitted from the sun actually hits the Earth? You could actually do the math and answer that question. But the answer is not very much. We're really tiny, we're really far away. Most of the light that the sun emits goes everywhere other than at us. And we're worried about carbon footprints. We should be worried about carbon footprints, but I'm just saying. This is small potatoes. One calorie. That's a term you guys are probably more familiar with, right? 1 calorie? That's 4.184 joules. It's an exact number. A kilocalorie. That, by the way, is when you talk about calories on your food, that's what those are. Do not confuse the calories on your food labels with the calories that we talk about in here. A calorie, you haven't defined that yet. Yeah, we did, right here. A calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water, otherwise known as 1 cubic centimeter, by 1 degree Celsius. So what would a kilocalorie do? It would either raise that 1 gram of water by 1,000 calories, which it actually wouldn't because of conversion, but we'll talk about that in a minute. But what it could do is raise a liter of water 1 degree Celsius. Let's do a little bit of math, just in case I haven't, guilted myself enough about my bad diet. This bottle of Powerade has 1 serving, 130 calories per serving. That's 130 kilocalories. That means that the sugar in this bottle of Powerade would be enough to take a liter of water from 0 degrees Celsius to 100 degrees Celsius and have a lot of energy left over to spare. A lot of energy. Measure out a liter, put it on your stove, turn on your stove, and see how long it takes to boil. That's what's in this bottle of water, Powerade. This is Mountain Dew, it'd be even worse. And I keep drinking it. So here's our conversion factors from calories to joules. So we can do some math with that later if we needed to. 1 hour of swimming, depending upon who you are, I imagine, uses around 2,100 kilojoules of energy. So the learning goal here for 3.5 is to use energy values to calculate the kilocalories or kilojoules for a food unit. How do we do that? Pretty much just did, just without specific maths. Carbohydrates are our primary fuel source. If we can, as mammals, we will burn carbohydrates preferentially to either proteins or lipids. In fact, we are so bad at burning lipids that before we burn those lipids, we will convert them to carbohydrates, which is stupid. But we didn't evolve to burn lipids. We evolved to burn carbohydrates. There is a bird. It's a finch, so it's not a big bird. Next time you're at a gas station, pick up a king-size Snickers. And look at how many grams of fat there are in that king-size Snickers. There is a bird. It's a finch, so it's a small bird. But it flies non-stop from Maine and northern Canada over the Atlantic Ocean to Brazil on one king-size Snickers bar worth of fat.
Unladen?
An unladen bird, yes. Aside from the ladenness of all of that fat that it's carrying to burn. But still, that's nuts! It's a lot of energy. Non-stop. There's no like layover in the Seychelles or something. They don't stop in Cuba for a little while. Just all the way down. They do that twice a year. I don't understand birds. Carbohydrates are our primary fuels. Next is fats. Last is proteins. So when we look at our food labels, we have our calories up here, which is actually a kilocalorie, otherwise known as a calorie with a big C. When you're looking at your food labels. So 1 calorie is 4.184 joules, right? So 1 kilocalorie is exactly the same number of kilojoules. Remember when we talked about straight conversions before? Grams per mil is the same as kilograms per liter, right? We just add a prefix to both, it stays the same. So 1 kilocal is 4.184 kilojoules. So 1,000 calories, 4,184 joules. Right? How do we figure that out? A relatively complex process that pretty much involves doing exactly what I just told you I did in high school with the Dorito, except somehow capturing all of that heat. We take a portion of the food that we have, we put it inside a container with some wires to ignite it, with an oxygen to burn. We burn it as much as we possibly can until it's completely burnt out, and then we measure how much it changes the temperature of a known volume of water around it. Because that's what a calorie is, right? The amount of energy it takes to change the temperature of 1 gram of water by 1 degree Celsius.
I always wondered, does the food have to be completely dehydrated?
I don't think it usually is, but it's burned to an extent with impure oxygen that it pretty much carbonizes everything. So the water itself isn't going to burn, but it's also not going to add to, it's not going to be fuel for burning type of thing. So it's a good question, but you have to ask a person who does this. But I don't think so. Carbohydrates have 4 kilocalories per gram. Fat has 9 kilocalories per gram. Protein also only has about 4. This is only one significant digit here for our kilocalories. Fat has a lot more energy. It is much more energy dense than carbohydrates. Once again, birds can burn fat directly. They get access to that full 9 kilocalories per gram. When we do it, we take that fat and we, for the most part, break it back down into carbohydrates, spending energy to do so, so that we can burn carbohydrates.
Keep our brain alive.
What's that?
Keep our brain alive.
Yes. Well, depending upon when it is that you're talking about this, yeah. The brain is...
2 days in when you're fully into metabolism.
The brain is the most second to the heart, I think, is the most energetically costly organ in your body.
You can actually starve if you eat between 100 and 800 calories. So people get into trouble doing juice fasts because they do vegetable juice, and they're over 100, so they don't go into metabolism, but they're under the necessary amount to feed your brain. So your brain actually starves.
Because it doesn't actually kick into remetabolizing fat into carbohydrates?
The ketones, yeah.
Yeah, ketone, yeah. Yep. So, we can do a little bit of math to calculate the energy type for a food when its mass is known, right? So here we have the amount of carbohydrates, fat, and protein in all of these potential sources of food. If you knew how many grams of carbohydrates, how many grams of fat, and how many grams of protein you had, could you calculate how many kilocalories there were in that parcel of food? Could you tell me how much energy is in 1 cup of carrots? 11 carbohydrates per gram. How many kilocalories per gram of carbohydrates? 4.
Is that including fiber?
We can't digest fiber. So it's the available energy to us. But that's actually a good question because fiber would still burn in a calorimeter. So I don't know. 0 fat, so that makes that math easy. 2 grams of protein per cup of carrots. How many kilocalories per gram is there in protein? Same as carbohydrates from that table, right? Just 4. Would you be able to do that math? Okay, just checking. Losing and gaining weight. The number of kilocalories or kilojoules needed in a daily diet of an adult depends on the gender, age, and level of physical activity. Generally speaking, you will lose weight when your food intake is less than the energy output. This is one of the reasons why men have an easier time losing weight than women do. Because by and large, we have more muscle mass. I say by and large because any given particular comparison, it wouldn't be hard to find a guy who had very little muscle mass compared to a woman who did, right? Compare Serena Williams to I don't care who. Well, most. But still, on average, muscle is expensive. Just sitting there. Let's say that you stayed exactly who you were and changed nothing else about your diet, but somehow I magically add 30 pounds of muscle in appropriate fashion to your frame in some manner. You will burn more calories sitting in that chair listening to me ramble on for 3 hours than you did before. Because just maintaining that muscle costs energy. You lose weight when your food intake is less than your energy output, in general. But here's the thing. It is really easy to eat way more than your energy output. Because food is, especially bad food, is relatively inexpensive. Easy to get. And unfortunately, we're addicted to sugar, which is a totally other biological thing that I don't have time to talk about. Moderately active versus highly active, females versus males. A highly active male in 19 to 30 should get, or should use typically around 3,000 kilocalories per day. Think about that for a second. Let's take a moderately active, young-ish female. 2,100 kilocalories per day. Put that in terms of boiling water. How many liters of water could you take from 0 degrees Celsius to 100 degrees Celsius? Which I should remind you does not actually make it boil. in 2,100 calories, 2,100 kilocalories. Each one of those kilocalories is enough energy to raise a liter of water 1 degree Celsius. That's what a kilocalorie is. Ladies, you guys just sitting here, falling into that 19 to 30 category in a moderately active state, which is making some assumptions. 2,100 kilocalories a day. Just being you, as a moderately active person, is enough to raise 21 liters, right? Because each one of those is enough to raise 1 liter, 1 degree. That's what a kilocalorie is. So 2,100 divided by 100, what is that? 21. You just being you burns enough energy to raise 21 liters from 0 degrees Celsius to 100 degrees Celsius in a day. That's how much energy it takes to be you. You guys ever looked up what The Rock does in a day? He has like 6 meals, has, I think it's over 6,000 calories. And then what he does for his workout is enough to burn through all of that in a day. Add on to the fact that he has a lot of muscle mass to pay for in the first place, of course.
People training for the Iditarod will eat beaver fat. It's the most calorically dense food stuff.
Yep.
And they use it all.
Oh yeah, come back emaciated. All right. Specific heat. Specific heat is another one of those things that water is surprisingly good at. It's another property of water, similar to the density of water as it cools off, but why frozen water floats, the mechanism of which we have yet to discuss, but we will. Water also has a very high specific heat relative to most other common things. When does the public pool open? It's usually Memorial Day. A lot of people like to go swimming on Memorial Day. Anybody ever done that? Gone to a public pool on Memorial Day?
It's freezing.
It's freezing! The water's cold! Even if you've had a week of warm weather beforehand, that pool water is going to be cold. You could walk out there and the sidewalk could burn your feet, and you get in the water and you're like, that's cold! Get back out. Stand on the foot burning sidewalk. Splash some water on it, cool it off. Why? Because water has a very high specific heat. Specific heat is different for different substances, but it is conceptually the amount of heat it takes to raise the temperature of that substance by 1 degree. Hold on. Where have I heard that before? What do we call a calorie? The amount of heat it takes to raise a gram of water by 1 degree Celsius. What's the specific heat of an object? The amount of heat needed to raise the temperature of exactly 1 gram of that substance by exactly 1 degree C. This does not mean that calories equal specific heat, except that a calorie is a measure of the specific heat of water, specifically. Which is why, when we do this calculation for water, what do you think the specific heat of water is going to be? Because the calculation is 1 calorie to raise 1 gram. So what is it? 1 calorie per gram? Or 4.184 joules per gram. So what's the specific heat of 24.8 grams of a metal if it absorbs 275 joules of energy? And the temperature rises from 20.2 to 24.5. Let's work this out. we have the time to do it, and we haven't done much math. We've talked about doing math so far than that, but we haven't done much math. So let's do some math. So what do we have? 24.8 grams of metal, right? It absorbs 275 joules. And the temperature rises from 20.2 to 24.5. What's the first thing we need to do? Before I advance to the slide that tells you, what's the first thing we need to do? We know what we have now. What do we need? The answer is specific heat, right? Now to make this easy, we can keep this in terms of joules, or we can do it in calories. But what is specific heat? The amount of heat, otherwise known as energy, needed to raise the temperature of 1 gram by exactly 1 degree. So, what is that? It's energy over gram degrees C. That's our unit for specific heat. Everybody follow? Energy in either calories or joules over 1 gram per 1 degree, right? Heat over mass times the change in temperature. So what do we have here? What do we have? What have we been given? We've been given mass, right? 24.8 grams. Have we been given heat? Heat is just energy. So do we have an energy reading here somewhere? 275 joules, right? So what do we still need? Change in temperature. So what's our change in temperature? 24.5 minus 20.2. So if we take 275 joules and divide it by 24.8 grams times 4.3 degrees C, what's that going to be? We could either do it or we could just advance here and see what it is. So have we done all of this so far? We've done this, right? If you want to plug it in, somebody wants to plug it in, I'll wait and we'll write it down. So what is this? What is the book telling us to do? We write down the givens. 24.8 grams of metal. That's our mass, right? 275 degree joules of energy. 275 joules of energy. The initial and final temperature. We need the specific heat, and so we have to connect all of these terms. So the first thing they're doing here, calculating delta T. Calculating the change of temperature, right? Which we just did right here, right? 24.5 minus 20.2. That was our 4.3 degrees C. We seem to be doing everything right so far? So, specific heat, abbreviated capital SH, is heat over mass times delta T. 275 over 24.8 times 4.3. Why is the answer given here only in 2.6 joules? Because what's our smallest significant unit here, significant figures? 4.3 only has 2 significant figures, so our answer should only have 2 significant figures. And so if you do the math, it rounds off to 2 significant figures at 2.6 joules per degree Celsius. Now, before I advance this slide, tell me, is that high or low? I ask you this question because I want you to appreciate something. You're on a beach in June. What's warmer? I said, you're on a beach in June at 3 o'clock in the afternoon. Forgive me, we're in Missouri. We don't have beaches here. We have things that pretend to be beaches.
Don't get Osage Beach.
We have things that pretend to be beaches.
Not even close.
What's warmer, the water or the sand? Sand. Where is the energy coming from that heats both the water and the sand throughout the course of the day? The sun. Is it applying the same amount of energy to the water and the sand? On a per surface area unit, yes. So what is heating faster? The sand. Does that mean it has a high specific heat or a low specific heat? Low. Why? It takes less energy to get that same temperature change. Or the same energy gives you a larger temperature change, right? So, that is in joules. 2.6 joules. Ouch. So now here's some math that this is not telling you how to do. Do it for me. Is the specific heat of this unknown metal more or less than water? You should be able to answer that question right now without doing any math at all. Why? It would require you to remember one little conversion factor though. Let me back up to it. This is specific heat in terms of what unit? If I were to write this out, what was it, like 2.6? 2.6, right, was the answer? But what are the units that I would have? I want to crawl into this space right here. What are the units that I would have? 2.6 what? Joules over grams degrees Celsius. Why am I writing all of those things out? Because when I did this math, there was nothing here that would let me cancel it out, right? If there had been mass on the top, 14 grams, then I could cross out that gram and cross out that gram, and it would just be joules over degrees Celsius. But that guy wasn't there. This is not there. We have nothing to cancel out any of these units, and so we keep all of those units, right? This is just algebra. If it was x, y, and z, we'd still have x, y, and z, right? So, 2.6 joules per gram Celsius. What is the specific heat for water in joules per gram Celsius? 4.184. So is this lower or higher? This is lower. Okay, it's lower. So, now, think about this for a second. Does that mean it would heat up faster or slower than water? Faster. Just like the sand. Question?
Are we ignoring all the trap data?
What trap? What do you mean?
There's space between the grains of sand. Those are there. It's not moving. It's highly insulated.
Very high surface area, allowing for a whole bunch of convection for loss of heat? Sure. But that's also getting a lot more complex than we would need to. Because theoretically, the water would also be giving convecting away a lot of heat every time it rolls over. It would be increasing the surface area of the water from every time it has a wave that comes through. Like there's a lot of different things where we lose. And so we have to keep it simple, conceptually. All right. Does everyone understand what we just did? Specific heat is one of those conceptual things that it's easy to get backwards. It's easy to misunderstand what this is. Specific heat is a measure of how much energy it takes to warm something up, to raise its temperature, right? Our standard bearer, much like a lot of the other physical properties that we've talked about so far, is what? Water. How do we measure what a degree Celsius is? A change in temperature of 1 gram of water. How do we measure what volume is? Based on a specific unit of an amount of water under specific pressure, right? Water is this standard bearer for a lot of the things. We use it as the benchmark for a lot of things. Water has a specific heat of 1 calorie per gram per degree Celsius. If your specific heat is less than that, then that means that the same amount of heat will give you, the same amount of energy will give you a bigger temperature change. Let's put this in different terms. Let's put a little bit of water in a pan on your stove. And put a little bit of something else in another pan on your stove. And let's set the stove, both of these burners, to be exactly the same temperature. What is going to warm up faster? The oven is warming both of these pans with exactly the same input of heat, right? What is going to warm up faster? If your specific heat of pan B is less than water, if the value is less than water, then you will warm up faster than water. If your specific heat is higher than water, then you will warm up slower than water. High specific heat means that you have the ability to absorb a lot of energy without a commensurate change in temperature. But it works both ways. That water that takes a really long time to warm up in the morning at the pool or the lake or the beach. Anybody ever gone night swimming before? In the heat of the summer, that beach can get cold. But suddenly that water is nice and warm. Why?
It takes more energy. It retains the heat better because it is a higher.
That beach heated up really fast, right? But that also means it's going to cool off really fast. That water took a long time to heat up. But that also means it's going to take it a long time to cool down. How much energy would be released by cooling 28.4 or 24.8 grams of metal from 24.5 degrees Celsius to 20.2 degrees Celsius? Could you do that math? If I told you that the specific heat of this metal was 2.6 joules per gram Celsius, could you do that math? Because you already have the answer right there. 275 joules. Specific heat is a property of matter. Different matter has different specific heats. Water is very specific. Ethanol has a different specific heat. In fact, let's get past our example and take a look at some. Here's water. 1 calorie per gram degree Celsius. Look at all of these things that are less than 1, which means all of them would do what? Warm up faster or slower than water? Faster. Pretty much everything on this, literally everything on this table, has a specific heat that is lower than water. Including our mysterious metal, right? But once again, don't get confused by the 2.6 because that 2.6 is on which of these scales? Our 2.6 that we got from that equation is in the right-hand column. These are exactly the same numbers. They are equivalent numbers. It's just instead of calories on the top, we have joules on the top, right? But they're just as interchangeable as a kilogram is to a pound or an ounce, right? And this math works both ways. The amount of energy it takes to warm up an object is exactly the same as the amount of energy that you would get if that object cooled back down. Now I'm sort of lying to you here because in a really complex system we'd also have to take into account entropy and where you're losing it to and all sorts of other jazz, but we're not going to worry about that yet. Coastal cities tend to have more temperate climates. I say tend, but you can find a nice coastal city off northern Greenland, and maybe this doesn't really apply. But coastal cities tend to have more temperate climates. Their temperature change tends to be more evened out than inland landlocked areas like Missouri. Why? Because during the day, all that water is absorbing a lot of heat instead of heating up the city. And at night, what's all that water doing? Letting go of a lot of that heat. So the city doesn't cool off quite so fast. This is just a whole bunch of ways that you can alternate or exchange the specific heat calculation. It's just algebra. All you have to do is the same thing we've done before. Take what we know, decide what we need, figure out what it takes to get there. What would be the extra step? If this was a If this was a fill-in-the-blank or multiple choice question on, say, homework or an exam, but the answers weren't in joules, the answers were in calories, what would you have to do? Take 2.6 and multiply it times a conversion factor that converts joules into calories. So you'd have 1 calorie on top is equivalent to 4.182, something like 4.186, something like that. Joules. The joules would cancel out, and you'd be left with calories. And what would that be? 2.6 divided by 4.1 something, I mean we'd have a specific heat in terms of calories of around what? 0.56 something maybe? So where would our metal fall? Pretty good, actually. Better than aluminum, right? Better than all of these metals. Look at this guy. Copper, 0.092. Silver's even better, 0.0562. We've got gold, 0.0308. What did I mention at the beginning of class? Heating. What could you do if you wrapped $1 around copper? Dollar wouldn't burn. Why not? Because the heat that it takes to actually burn that dollar bill, it wouldn't stick around in the dollar bill, would it? That copper would suck it away. Why? Now you can tell me. Why?
No specific heat.
Because copper has such a low specific heat. It takes very little energy to raise the temperature of copper. It's going to absorb that temperature, that energy very, very quickly. But what would happen if you kept that copper tube with the dollar wrapped around it inside that candle for a little bit? Eventually that copper is going to get hot. And then the dollar bill is going to start to burn. Right? Let's do it one more time. I'm seeing some I'm getting it faces. I'm also seeing some I'm not sure if I'm getting it faces. So, using the heat equation, let's calculate the energy in kilojoules needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. All right, what do we know? We know mass, right? 255 grams of copper. All right? We are heating, so temperature initial is 24 degrees C, temperature final is 185. So what's our delta T? 161 degrees C, right? Let's keep our units because those might be important, and by might I mean are. So that's what we have. Our equation is specific heat is equal to energy over mass times delta T, right? Let's back up and make sure we're right. Heat or energy over mass times delta T. Yep. So, right now, what do we have? We have, this is what we want, right? Specific heat. That's our unknown. Isn't it? Or am I wrong? What do we have over here? We have mass. We have delta T. This is actually our unknown, isn't it? The question is asking for energy. But we don't know the specific heat either, do we? Or do we? Can we look it up?
Since it's a 0.385, is that what it is? Since it's copper?
0.385 would be in joules per gram Celsius. But our question asked for something very specific, didn't it? It asks in kilojoules. So yes, we should use this one, not this one. Because if we use the calorie one, what would we have to do? Just convert it to joules later, right? So we'll use the joules one. Where's our copper? 0.385. So, specific heat. This is a known now, right? It doesn't tell us this in the question, but we have a resource to look it up. So the specific heat for copper in joules per gram Celsius is 0.385. Can we solve this now? We have 1, 2, 3, 4 variables, right? We have 1, 2, 3 of them as known, right? This one is known, this one is known, this one is now known. So if we plug that in, first off, what are we solving for here? Energy, right? So before we start plugging in numbers, let's do a little algebra. What do we got to do? We have to move our mass and our delta T over to the other side, right? We have to get them out of the denominator because we want energy by itself on one side. So energy is equal to specific heat times mass times delta T. Everybody follow that? So now we can plug in these numbers. 0.385 times our mass, which is 255 grams, times our delta T, which is 161 degrees C. I'm going to move this over for just a second because I want you to see something. Our specific heat of copper is 0.385, right? But that's not what we should write down. What should we write down? To make sure we're doing this right.
Is there a point for that?
No, we can put 0.385 because that's a given number. It's an exact number for something that we have from that table. But we have not yet written down units. What's the units for specific heat? Joules over grams degrees Celsius, right? Why did I write that down? Because this is a way for us to double check that we're doing this correctly. We now have grams and degrees Celsius in the denominator. But this is all over 1 and this is over 1. So what can I do with this gram and that gram? They cancel out, right? The 255 stays there, that's fine, but my g's go away. What can I do with that degree C above and that degree C down below? They cancel out. The 161 stays the same. So what am I left with? What unit will my answer already have? Joules. And what is my answer? What does my answer need to be? It needs to be in joules, right? Specifically kilojoules, yes. So if we wanted to, could we do that math now? What would we need to add to turn joules into kilojoules? So what's our conversion for joules to kilojoules? 1 joule is 1,000 kilojoules, right? But we need the kilojoules on the top, because that's the answer we want, right? So, how many kilojoules in 1 joule?
1,000.
Careful.
Oh,
Oh, how many?
How many kilojoules in 1 joule? So, or we could keep it the same way. 1 kilojoule is how many joules?
1,000.
There, that works. Or what's another way you could have written it?
1,000 joules over 1 kilojoule.
You could put 1,000 joules over 1 kilojoule, yes, but what would that do? If we did it that way, I'm leading you, but that's
Well, yeah, you would be able to.
right. So if we did 1,000 joules up here, that would leave us with joules squared over kilojoules, and that wouldn't be good. That's not what we want, right? So we could write this as 1 joule over, 1 kilojoule over 1,000 joules. And that is perhaps where I should stop, because that is exactly what we have learned so far to do, right? Right? That equivalency. Okay? Could I also write this? If you look at that up there and you go, wait, what? And your mind kind of breaks, just pretend it's not there. How did I get that number up there?
So if you divide by 1,000.
Yeah, I just divided both numbers by 1,000. So 1 kilojoule per 1,000 joules. Over 1,000 joules divided by, do you see that? Let me get out of the way. I'm writing because it's convenient, but this is probably where no one can see it. I should be doing this over here. Question?
5 is 1 J.
1,000 J over 1,000.
0 point, like 0.001. I'm just trying to read that. Okay, I'm sorry.
No, that's fine. That's the problem with writing on the board. If you can't see what my things like, half of the point of this discussion is just that you can see these labels, right? So it's good that you clarify to make sure. I don't want to confuse you. So you could write this, because all that's doing is dividing by 1,000, which is exactly what this is going to do, right? Divide by 1,000. So let's forget about that for a second. I'm just showing you that there's more than one way to skin a cat. It's all just algebra. As long as you do it the right way, it's all right. It's all good. So what's going to happen here? Now this joule and this joule cancel out, right? And so our answer is going to be in kilojoules. So this right here is an exact equivalency. 1 kilojoules over 1,000 joules. So it does not affect our significant figures at all, right? Because it's an exact equivalency. Otherwise, we'd be in trouble, right? Because that 1 kilojoule would tell us we can only have one significant figure. Right? But it's an exact equivalency, so it doesn't matter. So what do we have here? How many significant figures here? 3, because that first 0 doesn't count because it's just holding the decimal, right? So there's 3 significant figures here. How many significant figures in 255? 3. 161? And we just said that none of these mattered, right? Because it's an exact equivalency. So what should our answer be? 3 significant figures. Somebody want to do that math? Because I don't have like a calculator in my
I
head.
got 15.8.
15.8? And that would be what? Kilojoules?
Oh,
Are we all agreeing 15.8?
yeah, she pointed out to me it's on the next page.
Oh, yes. Which is why, it is, yes, you are correct. Which is why I have not advanced to the next few pages. 15.8. So if any of you were cheating when you looked forward, we didn't cheat up here, right? I wasn't looking at these slides. If you followed along without looking at the slides, then did we all get there? Do we all understand it?
Homogeneous alloy, would it behave like you would expect it to behave? Or like I always think?
I honestly don't know. A homogeneous alloy, I would expect, would need its own defined specific heat. Because the problem is, you could say, well, a homogeneous alloy of exactly half this and exactly half that, you could probably calculate the specific heat. But the problem with a homogeneous alloy is that that guy's brass from that foundry and that guy's brass from that foundry are probably going to be almost exactly the same, but maybe not exactly the same.
Cooled with different matrices.
Or literally just a percentage different amount of this versus that.
I'm confused about how you got 15.8. Is it just that around the decimal place? Because every time I calculate it, I get like 15,806.
Let's try.
Divide by 1,000 at the end. Okay, yeah, alright.
Right, so your answer was in joules, which is correct. Like, that's the first step, yes. But because this is just math and we understand what we're doing, you can put this equivalency here and plug it in right into your thing so that your answer comes out in kilojoules. But yes, if you were getting 15,800 or something that would round to that, then yes, you just divide by 1,000 and that gives you your answer in kilojoules instead of joules. By the way, somebody tell me, this is going back to chapter 1 and chapter 2, and because we have time, somebody tell me, what would this number be in scientific notation in joules maintaining degrees of significant figures?
1.58 times, is that what you're asking?
Yes, 1.58 times 10 to the what?
Well, no.
First off, if we need this in joules, what would it be again? Not 15.8 kilojoules, but what?
15,800 blah, blah, blah.
All right, now turn that into scientific notation.
Well, 1.58 times.
10 to the 4th, sorry.
Yeah.
1, 2, 3, 4.
My defense.
It's really far away, it's okay. And I'm not writing really big. This is not like see from the back of the room size font, really, right here. Like I said, that's throwback to chapter 1 and chapter 2. Not in sort of chapter 2, converting it back to joules is sort of chapter 2.
So what was your original question, just so I...
What would this be in scientific notation as joules,
Joules, okay.
maintaining significant figures? Because 15.8, like, it would turn into 1.58, not 1.6.
So what if you would have asked, what is this in significant figures, or what is this in scientific notation in kilojoules?
Then it would become 1.58 times 10 to the 2. Yeah.
Would it be 2 or is it 1? Because it's going to be 1 over.
Well, the problem with 10, yeah,
Just don't ask that. How's that sound?
Yeah, it would be 10 to the 1, wouldn't it? Yeah, times 10. Yeah, 10 to the 1.
Okay.
Yeah. 1.58 times 10 to the 1.
Okay.
Yeah, that screws with me because you never, like, something that small you don't put in scientific notation, so you don't think about 10 to the 1 very often. All right, so. Oh, shoot, we have a lot. Was that? No, we're lot more of this chapter, doesn't it? Where am I?
Change of state,
You just say
Yeah.
3.7.
right there.
Yeah, okay. 63 of 82? More than I thought. But still, from the number of odd looks I was getting, I feel like we needed to maybe focus on this for a little. Do we need to take a break?
Can you just power through?
Power through? Everybody cool with that? Powering through? Good. Because I'd really like to not have to deal with 10 pages of this chapter at the beginning of class on Tuesday. All right, so change of state. This is going to involve some more math because here's the thing. There's a reason why when I've been talking about calories and diet and everything, and I've said, okay, how much does it take to raise, it's enough energy to raise water from 0 degrees to 100 degrees. Because, and I didn't just say boil, you can raise it from 0 to 100, that's fine, that's straight, that's easy math, right? But going from 100 degrees to 101? Can you have liquid water at 101 degrees?
Well, what degree Celsius?
Celsius, yes. Good question.
Would be boiling, right?
It would be beyond boiling at 101.
Well, I guess it'd be.
It would already be boiled. Unless, of course, you're talking about water under higher pressure, in which case you're breaking the question. Because yes, you can get water at above 100 degrees. In the same way you can get water below 0 that's still liquid, but not under normal conditions. So, to get to 101 degrees, the water has to boil. It has to become a gas. And changing from a liquid to a gas requires energy. So that jump from 100 to 101 is a lot more energy than the jump from 99 to 100. Everybody follow? And the same thing happens at the melting point. Going from -1 degree Celsius to 0, and then turning into a liquid, that change of state from solid to liquid takes a lot more energy than simply bringing water to 0 degrees, warming it up a little bit. A change of state. A state is this a physical or chemical change? Everybody agree? Physical change. Water is still water, regardless if it's liquid or solid, right? So this is a physical change, not a chemical change. To go from one state to another requires a lot of energy. So, the melting point of water is the same thing as the freezing point of water. Where does water melt?
Surface.
At its surface, at 0 degrees. If water at its surface is at -15 degrees, is it melting? No, it's still at -15 degrees. You add heat to it, it's just going to get a little bit warmer. Now it's -13 degrees, -10 degrees, right? It's warming up. It melts when it reaches 0 degrees. So what is the only temperature where you can have water as both a solid and a liquid under normal conditions? Right at 0. In the same way that you can have water that's 100 degrees as both a liquid and a gas. Not at the same time.
Okay.
This molecule is a gas, this molecule is a liquid, right? It's not like one atom can simultaneously exist as both. I don't mean to confuse you in that manner. But some of the liquid, some of the water at 0 degrees can be solid, and some of the water at 0 degrees can be liquid.
This is why you get like slush.
Yes.
It's a process.
Right, that perfect moment, right at 0. Because here's the thing. Have you ever noticed when you're boiling water that you don't, sometimes you get a hot spot, and that's cheating, I'm not talking about that, but when you boil water, what's the process? You put water on the stove, you let it heat up, blah, 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 you start seeing little bubbles forming on the bottom, but when it finally starts boiling, it just kind of goes, right? It doesn't boil just at the surface. It doesn't boil just on the edges. It's going to boil where the heat is being added, which unfortunately in this metaphor is the bottom, but it's boiling everywhere. You don't get like the left side of the pan boils and the right side of the pan doesn't, unless your pan is lopsided. But point is that we're getting heat everywhere. It has to heat up everything. All of that water has to be at 100 degrees before it will actually boil. Because if there is any that is not, if you add a little bit of even warm but not boiling water to water that's about to boil, what happens? Next time you're doing this, do a little experiment at home. Take some, don't use cold water because splashing is bad, but take some, warm water from your tap. Get your water, you're making mac and cheese for your kids, whatever, warm it up, cooking some pasta. Wait until it's right at that point where it's about to really start boiling, right? Like you're seeing the bubbles on the bottom, and it's like a few of them are starting to rise. Take that bit of water, just pour it right in there. All those bubbles, gone. Why? Because all the heat that all the water that was already there had, when it came in contact with water that wasn't that hot yet, what did it do? It donated some of that heat to the not quite as hot water, which means all of the water isn't right at 100 degrees anymore. Now it's a little bit lower. At 0 degrees, you can have both solid ice and liquid water. And you will not have all liquid or all solid until it is all liquid or all solid. None of that 0 degrees liquid is going to warm up to 5 degrees until all of the ice is melted. If you're cooling it off to freeze it in your freezer, none of that ice will drop below 0 until all of the liquid has frozen. Because it is always going to give or have energy donated to it. The cold thing will always get energy donated to it from the warm thing until everyone is the same temperature. The melting and freezing points are the same thing. We can be both at the same time in one big conglomerate pot, right? But once again, not the same atom. The heat of fusion, which is perhaps poorly named, because when I think of fusion, I think of stellar phenomenon, I think of fusion of molecules. Really what we're talking about a heat of fusion here is, we're talking about the fusion of otherwise liquid molecules fusing together to form a solid. And what is a solid? It has defined shape, right? So we're fusing into a chunk of ice in the case of water, instead of liquid water that just flows. The heat of fusion is the amount of energy that must be used to convert exactly 1 gram of solid to liquid, or vice versa, at the melting point. And in this case, it's 334 joules. Let me ask you a question. What's the relationship between this and the specific heat of water? What's the specific heat of water in joules? It's 1 calorie per gram degree Celsius, or 4,000 something or other joules per gram degree Celsius, right? So, we're not changing a degree at all here. We can't use the specific heat equation, because there is no temperature change. Delta T is 0. Water that goes from solid to liquid or back is not changing temperature at all. It is changing state. But what is the relationship? Does it take a lot more energy? Or a lot less? 334 joules will convert 1 gram of ice to liquid, or removing that much energy will convert 1 gram of liquid water to ice. The specific heat was 4,000. So it doesn't take a whole bunch of energy. This is less than the specific heat, right? So it doesn't take a whole bunch of energy, but it still takes some, where there is no temperature change at all. And there will be no temperature change until all of the water in question is ready or has gone through that change of state. So, 334 joules or 80 calories, not kilocalories, but 80 calories. That's melting. Why is this the same number? Heat of fusion for here, heat of fusion here. Okay, so we have quantity, 1 gram. Oh, sorry. Oh, we moved on something else. This is the same number because this is still just the same amount of energy going back and forth. Here, heat is removed to freeze it. Here, heat is added to melt it. Follow? But it's the same number. 80 calories or 334 joules. 80 calories or 334 joules. It takes exactly the same amount of energy to melt something as it does to freeze something. In the same way that it takes exactly the same amount of energy to heat something up as you get back when you cool it off. Everybody follow? So here are all these conversion factors that we can do. 80 calories per 1 gram or 334 joules per 1 gram. So how much do we have? Times the heat of fusion, that's how much heat we have to gain or lose to convert the whole thing. Do you see a practice problem coming up? How many kilojoules are needed to melt 32 grams of ice at 0 degrees Celsius? How would we do this? I'm not going to spend a lot of time on this because I have a lot of slides to get through, but also because we should be able to do this, right? We just did a whole bunch of things just like it. We just don't have a delta T here. We have mass, right? And we know we're at 0 degrees C. Why is that important? What if this question said how many kilojoules are needed to melt 32 grams of ice at 5 degrees C? Ooh, darn it. I thought I said I was going to do this quickly. What would that change here? What would we have to do first? Before we can melt the water, what do we have to do? Or, this is melting, sorry, at negative 5 degrees C. So what if we have ice that's not at 0? What if you have ice that's not ready to melt? We have to heat it up first. What would we need then? That specific heat equation?
Oh, yeah.
The thing we just talked about, right? And then add on a little bit more energy to actually melt it, right? But let's start with this. We have water, it's ready to melt. We've got 32 grams. 32 grams of ice. We need kilojoules, so there's a little bit of conversion there because our conversion factor before was not in kilojoules, it was in joules. So here we go. Here's our conversions. And here's our math. 32 grams of ice, right, as a solid, that's what that S means, times 334 joules per gram, right, times our conversion factor of a kilojoule per 1,000 joules. This looks really familiar to me. Does it look really familiar to you? Gives us 10.7 kilojoules. That's how much energy it takes to melt 32 grams of ice. That's kind of a lot of energy. So that's melting. There's something called sublimation. Melting is the process of going from a solid to a liquid. But there is a process called sublimation, where particles on the surface of a solid will change directly to a gas without going through the liquid state. But there's no change in temperature. The reverse process is called deposition. Where have you seen sublimation before? Dry ice undergoes sublimation. Sure. Yeah. So dry ice is a solid, right? And so every other thing that you've ever dealt with in your life, if it's a solid, when it melts, what does it become? A liquid. Don't you find that, you guys ever use dry ice in like, coolers and stuff? Isn't it so annoying when you've got all that liquid carbon dioxide on the bottom of your cooler? You ever had that problem?
It's fun.
Well, it's because it's not liquid. Dry ice doesn't melt to become a liquid. It melts and becomes immediately a gas. There is no liquid stage in between. That's sublimation. You've seen it somewhere else too. In the winter, when we have ice storms, we get ice on trees, and then the next day it never gets above freezing. What happens to the ice on that tree? Give it enough time, it goes away. You ever gotten ice, like those little frozen things on your windows? It's on the edges of your windows. That's deposition. But that can also disappear without actually melting. That's sublimation. An interesting thing, why do we add salt to our driveways when they get icy? It's to help the salt melt, right? Except that, have you ever gone out and looked at that ice as it melts from the salt? Does it turn into running liquid water? Sometimes it does if there's enough of it, but most of the time it just gets brittle and seems to almost just evaporate. Guess what it's doing? It's evaporating. It's sublimating. The ice crystals that you're dropping on that, everybody thinks you're adding ice because it changes the melting point of water and so it'll unfreeze or something. That's not why you're adding salt to your ice. The salt gives the water a matrix to sublimate and become a gas. That's why.
Is this all related to transpiration?
No. Transpiration is something that plants do.
I mean, sorry. You lose material off the surface of water.
That's just sublimation. Yeah. It's this.
Okay.
Yeah. It's sublimation, except you're just giving it a matrix. You're giving it a catalyst to sublimate. Has a lot to do with entropy, and we're not going to get into the math with entropy, but here we go. So, evaporation is when we take a liquid to a gas. Sublimation is when we take a solid to a gas, with no change in temperature. You'll note that there's not a big calculation here, right? Because it involves entropy, and we're evidently not involving entropy in this class yet. Be thankful. Entropy is a hard concept to wrap your head around sometimes. Evaporation, I could be wrong, maybe I'm just not remembering correctly. About once here. When we're taking liquid and turning it into a gas. That happens at the boiling point. Once again, all of this water in this beaker right here, it is heated up to 100 degrees Celsius. And then none of that water will get any higher. None of that water is at 102. If you took a chem lab and watched this happen, you could boil all of that water, and guess what would happen to that thermometer right there? It would never go above 100. As all of this water disappeared, all of the heat coming in from that Bunsen burner would be going into the cost of evaporating the water. None of that water would go above 100. It would stay at exactly 100 the entire time. That heat's going somewhere, right? But it's not heating up the water. It's paying for the cost of changing from a liquid to a gas. Now what happened if instead of a big Bunsen burner and a beaker here, what happened if this was actually a really big glass ball? Once all that water turned into water vapor, then what would that Bunsen burner start doing? Then what would happen to that thermometer? It would start climbing again. Because now that we're all a gas, we can start warming up further, right? Condensation is the opposite of vaporization. Condensation is when gaseous water turns into liquid water. You guys ever had like a problem? Oh, I don't know. I guess the easiest way to get this problem outside of like running your car through a flash flooding river is you go to the beach, you go swimming or whatever, you get into your car and everybody's like got blankets, the towels are soaked with water. The next day you get in your car and you notice something. Your car is really humid, right? From all that water, all those towels. What's the best way to clear it out? You want to turn on your heater? Burn all that water away? What's the best way to get rid of all that humidity in your car? Have you done this recently? What's that? Turn on the AC. My house yesterday, because I was really resisting turning on the AC, because I was like, oh, it's just the first hot day. I don't have to turn on the AC. By 8 o'clock at night, my house is at 78 degrees, and it felt like it was a sauna. I'm like, dude, turn on the AC. 5 minutes, oh, so much better. Why? Because the air conditioner, all those coils that were cooling down and running all that air past to cool down the air, what happens to air with a lot of water in it when that air cools down? The water condenses out of the air. Same thing happens when you got your cup with a lot of ice in it. Gets water droplets on the outside of your cup on a nice hot summer day. That's not because the water on the inside of your cup is spilling out and coating the outside. It's not leaking through the walls of your cup. It's water from the outside air condensing on the surface of your cup.
Could you also just have low surfaces?
What's that?
Could you also have, what's the word, the low surface?
Specific heat?
Specific heat, yeah.
You could, except that we can't change the specific heat of water because it's a fundamental property of
I'm
the
saying you as a person.
Hmm.
That's what I feel like as my husband.
Yes, our heat tolerance. That's a totally different thing. That's behavioral. Yes, yes. Heat of vaporization is the amount of heat it takes to change 1 gram of liquid to a gas. Or it's released when we take 1 gram of gas and bring it down to a liquid, right? For water, it's 540 calories or 2,260 joules of heat is needed to convert 1 gram of water into 1 gram of water vapor or steam. This can only happen at 100 degrees. So what takes more energy? Melting water or boiling water? Boiling. Melting took only about 300 joules, right? Boiling takes 2,000 joules per gram. But it makes sense, because it takes a lot of energy to make water stop holding on to each other and really spread out and become a gas. That same 2,000 joules would be released in some manner if you were to cool off a gram of water. We talked about this earlier. Why is it that taking, aside from the fact that it's a drug and you shouldn't do it, why is it taking ecstasy and then going to a rave where you're dancing around a lot's a bad idea?
Sweat.
Because you can't sweat and you overheat, you go into heat stroke. Okay, why does heat stroke, or why does not sweating lead to heat stroke?
So you can't cool down your body.
Because we use sweating as a means of evaporatively